First of all, I would like to thank you organizers and Andrea for opportunity to be here, because this is a really nice event with full of interesting presentations. So as was told, I will have a presentation on my former work about textural features and illumination invariance, and at the end I will add a short demo from my current work in Honeywell. I can go. So this work was done with my supervisor, Michal Heindl from Institute of Informational Theory in Prague, and I will start with these three pictures. This is three images of the same area captured during different light conditions. The first one was during sunny morning, the second one during the cloudy afternoon, and the last one during the night. And as you see, not only the colors are totally different, but there are other things like large cast shadows caused by directional light, also another shadows here, a kind of micro shadows in the grass, and all these appearance changes significantly complicates either segmentation of images and further understanding. If I go more detail into the texture level, here are three images of the same material. This is just a normal wall, at first lighted from the top, and then you can see as the light goes closer to the surface, the sample gets darker. This is quite known fact. More interesting is here. This is Polish wood with a lacquer on it, which can be found in kind of luxury cars, and I hope you can see as the light goes around this sample.
Shall I give them this?
Yeah, a little bit, please. Yeah, you can see it. You can see that as azimuth of the illumination changes, the color of these areas even swaps. This is caused by a very complicated light scattering between the Polish wood and the lacquer on it. So these are just examples how appearance of synthetic or natural materials may change. And if you try to recognize such materials, you have to deal with these conditions. So our approach was creation of features which are invariant illumination spectrum changes. I mean the color of the illumination source. They are approximately invariant to local intensity changes, and from experiments we know they are also quite robust to illumination direction changes. Most importantly, it works under unknown illumination conditions and with a single training image per texture. So the outline of the algorithm is following. We start with carbon level transformation to decorrelate the spectral planes in the image. Sometimes this method is called principal component analysis. Then we build a Gaussian downsampled pyramid on the image. This is the pyramid where each higher level is blurred and downsampled version of the lower levels. We use this pyramid to capture larger spatial relations in the texture. And each level of the pyramid is modeled by a Markovian type of model. We estimate the parameters of the model, and at the end the model parameters are transformed to be illumination invariant. And that's the textural feature we use. There is outline of the algorithm. As I said, starts with Gaussian pyramid, and then each level is modeled, and Illumination invariants are computed from that. And after that, all features are put into the feature vector, which is can be compared in an ordinary way. Now I will go more in detail into the modeling. We use a special type of Markovian model. Okay, so let's why are pixel at position R? This R is composed of row and column indexes, and why are just pixel values. In ordinary images, it's a free size vector composed of red, green, and blue, and we assume that pixel value can be expressed as a kind of linear combination of its neighbors. So these are the neighbors, and these are the unknown parameter matrices. In a RGB case, these matrices are 3 times 3. Plus some Gaussian noise, which is supposed to have zero mean and unknown covariance matrix. Why we use this causal autoregressive model? These models have its neighbors restricted to the upper half plane. So if there is the pixel, the model can use only these neighbors. This is one example, or we also use a bit larger neighborhood to the distance of 3. And if we are restricted to this type of neighborhood, the advantage is that Bayesian estimate of the parameters can be expressed analytically and recursively, which means that the parameter estimate can be done very effectively, going through the image from upper left corner down, and at each pixel position we can incrementally improve the estimate of the parameters. So that's how the model parameters are estimated, and now I will go more detail into illumination invariance. It's a known fact that if y are pixel value at some position R, the change of illumination color can be modeled by a multiplication with a matrix B, which is 3 times 3 matrix for this case. So that's how the image will change if we enlight the sample with a different illumination color. And this matrix B is same for each pixel position. And if we substitute this term into the equation for model parameter estimation, we can end up with these equations, which means that model parameters for different illuminations are similar in a mathematical way. And that's exactly what we needed, because this instantly implies that traces of these matrices and also eigenvalues are features which do not change with the illumination color change. We will derive a bit more invariants. This one looks a bit complicated, but it's not that case. This sum, in fact, is a value predicted by the model, and this is actual value So this term states how good model is in the prediction of texture, how good the model can explain the texture, which kind of says how much the texture is complicated. And also, I will not go into the details, but prediction probability and model probability can be made illumination invariant. As I understand, not all of you are from the computer vision, so I will briefly go through the alternative features which are used for texture recognition. One of these classic features are based on Gabor filters. Gabor filter is a kind of wave in a Gaussian envelope. This is how it looks in a 2D case. And the important thing is that if we compute Fourier transformation of this filter, we can see that it is very well localized in terms of frequency and orientation. This means that if you convolve this filter with your image, you get the edges under the certain scale and orientation. And you can construct more of these filters by scale of the filters and orientation and cover the whole spectrum of the image, or half of the spectrum, because the spectrum is symmetric. And that's why you get your textural features. Another nowadays very popular method is local binary patterns. Who knows this method? Okay, so this method is basically histogram of micro patterns. It works in a way that you have a central pixel, and you look at pixel neighborhood, and you look at which pixel values are greater and which are lower than this pixel value. And in this way, you get kind of it's a binary microtexture. And convert this microtexture into one number by multiplication with power of 2. And after that, you compute histograms of these micropatterns. And that's it. So that was the features. And now I will show some of our results and some of the databases materials, so we can see what are the possible variations in the database and what results could be expected. I will start with the database from University of East Anglia, which consists of 28 patterns that were acquired with 6 acquisition devices, or either scanners or cameras. And you can see that this one material has quite significant changes in appearance. Now, why this database is difficult? You see, these patterns have pretty similar colors. So if you would try to recognize it just based on the colors, it wouldn't work. Okay, so here are the results. Our results, which are in purple and red, goes from 70 to 90% accuracy for different number of training samples per each material. In this case, LB3 features, which usually works pretty well, kind of failed. The reason was that there was a slight change of scale in the database, and LBP features are not good at it. So this stats show how the features works in the change of acquisition device. Another example, I will show you the results on the database which consists changes of illumination direction. This is database from University of Bonn, The database was created for computer graphics, and especially for modeling the cars. The thing is that if you are trying to design the car, you really need to precisely model its appearance. It's not like in computer games where it just enough if it looks real, but you really need to model it as it would be created. Not only because you are going to build a real car from it, but also for the security simulations, because they are doing some tests as for example, as the car is passing through street, and you definitely do not want any reflections on your dashboard or any interior in the car which might temporarily blind you. That's why the database was created. We took material samples, illuminated under 80 different illumination conditions, was changing the declination and azimuth of the source. These samples shows how this kind of cloth, I think it's called fibers, as the illumination goes closer to the surface, and these four are as the illumination goes around the sample. And again, there are significant changes in appearance. For this particular example, our features work pretty well. The precision of recognition was almost about 97%, even with a single training example. The last result I will talk about is on Amsterdam Library of Textures. This is the currently best database of textures. So if you would like to do any work on textures, I would recommend this database, because it has color, high resolution images acquired by 4 different cameras, 6 illumination directions. Also the rotation of material are included, and 1 additional different spectrum. And more importantly, it has more than 200 different materials. And as you see, it has micro textures, kind of macro textures. Most of the materials are rough, which for this rigged paper, it means as the light goes around this paper, it really changes its appearance. This is lighted from the side, perpendicular to the ridges. This is with these valleys, and they are almost disappears. So a lot of variation. And to show the results, we achieved the precision of classification about 65%, using 8 training samples for material, and going down to 40% for 1 training material per sample. And this is like 20% better than the published result on this database. Well, why the results are not better? At first, there are like more than 200 classes, which is always a difficult problem. Then the training data have less variation than the test data, which kind of features need to extrapolate or be really invariant. And most importantly, as can be seen in this example, it includes different camera positions, which results in perspective transformation, and none of the features I compared or are widely used now can deal with these changes. So if we would only restrict ourselves to the same camera positions, like all the results of all features would be like 20% better. that was for the results. We applied our features in different applications. The first one was kind of toy application for content-based retrieval of ceramic tiles. The idea was simple. Maybe if you want to choose tiles for your bathroom, and if you are looking on some ceramic tile, the idea was that you may also like tile with a similar color or a similar style and texture, and the system was trying to help with that. We did a very simple experiment with people rating the retrieval results, like similar or very similar, and ended up with 60% people saying that the results were similar or very similar. Another application we did was invariant texture segmentation, but if you are interested in that, you can talk with me later. And very interesting application was in computer graphics, because in computer graphics the textures are pretty high and you have to compress them, and usually you have kind of tunable parameter which says how much are you compressing the textures. But the thing is that this parameter is usually not correlated with the human perception. So for some textures you can compress really high and users are not going to notice that, and some of the textures, only a slight compression, are easily noticeable by people. And a friend of mine did a psychovisual test where the people were rating these, like, oh, these two textures look similar, the same, well, oh, this is different, this one was compressed. And we have discovered that the features I have presented, or slight variation of that, has a high correlation with human perception or detection of the texture to be compressed, which means that the features can be used to predict and optimize the optimal selection of these compression parameter. And we also did some application glaucoma detection. Okay, so to conclude this short talk, I have introduced features that are invariant illumination spectrum and cast shadows, also quite robust illumination direction, Gaussian noise. But if I can choose one take-away message for you, it is that colors are really important, but in real-life conditions you cannot rely on raw measured colors. You either need to calibrate it if you have laboratory conditions, or you have to normalize it or take an invariance approach. So it means choose features which are invariant to these changes. Okay, well, maybe I have time. I can show you some demonstration. If you are interested, I have like online demonstration. No, I'm not connected to internet. Okay. So at these address you can really try the retrieval results. I have here the comparison with LBP, and you can play with the system and you can see which features consider what textures to be similar and what to be different. So that was my work on textures. If you have any questions.